So today we're going to continue talking about derivatives. If you have any questions, please raise your hands anytime. Also, I got a bunch of chocolate for you guys, so happy Halloween. A little bit late. So, okay, today the topic is 3.5 called implicit differentiation. So what does that mean, implicit differentiation? We're going to find out in a moment. Recall, first of all, we were talking about the chain rule last time. What was the chain rule about again? The chain rule is useful for derivating what? Compositions of two functions. So if f of x is equal to f of g of x, then f prime of x is equal to, this is the rule, it's the derivative of f multiplied by the derivative of g, but with a twist. Basically, it's the derivative of f evaluated at g, and then just the derivative of g. This is the twist. Not just f prime times g prime. So, for example, and we did a whole bunch of examples last time. So I'm going to give you an example today that is already a little bit more complicated. It's actually one that you already saw before. F of x equals u of x to the 5. So now, what I would like to stress in this example is that we don't know what u is. U can be any function. But u is the inner function in this case. So the outer function is x to the 5, and the inner function is u of x, and I don't know what u of x is, but I can still differentiate it. Let's see, so the inner function is u of x, and the outer function is x to the 5, right? And I can find out f prime of x, which is what? Well, let's see. So in our heads, let's derivate the outer function, x to the 5. The derivative of the outer function is 5x to the 4, right? So this is 5 times u of x to the 4, the inner function evaluated at the derivative, multiplied by the derivative of the inner function, u prime of x. Okay? So let me write this a little bit more casually. The derivative of u of x to the 5 is equal to 5 times u of x multiplied by u prime of x. We're going to see this more casual notation more in a moment. But for now, I would like you guys to understand what we're really doing is we are actually doing a chain rule, except that we don't know what the inner function is. And it doesn't matter. It's okay. To the fourth. Thanks. Okay, so, right. So now, let's put that idea to good use of finding derivatives that we don't really know on a well-known and by now hopefully well-liked function, which is the logarithm function. Do you guys agree that this identity is correct for all x? Why is that identity true again? Because ln and e are inverses. That's right. We've written this equation a few times already. So what I'm going to do is I'm going to derivate on both sides. Derivate on both sides. So the left side, because we have a composition, we're going to be using the chain rule. On the right hand side, I just get 1. Right? So let's do this a little more carefully. The derivative of this using the chain rule is, well, let me write it down one more time just to be more perfectly clear. The inner function is the logarithm function, log x, and the outer function is e to the x. So what is the derivative of the outer function? It's e to the x, right? So the derivative of e to the x is e to the x, so I write e to the inner function. And now I still need to multiply by the derivative of the inner function, the derivative of logarithm. Now you may know the derivative of the logarithm function, but in this class we haven't actually done it. We don't know what the derivative of the logarithm function is. Does it matter? Well, no. Think about logarithm function as u of x. It's just some function. If we can take the derivative of u of x, we can take the derivative of the logarithm function. So we write simply the derivative of the logarithm function, whatever that may be. And this thing is equal to 1. Right? Great. Now this tells us something really interesting about this derivative of the logarithm function. It actually tells us what it is. Because, as you know, e to the logarithm of x is just x times d dx of ln x is equal to 1. And that means that the derivative of ln x is equal to 1 over x. Shocking, right? Well, you already know it. Many of you already, who already knew this? Okay, many of you already do it. Okay, but I bet you didn't know how to figure it out, how to do it. So here's a very quick derivation that the derivative of logarithm of x is 1 over x. Right? I am actually jumping my gun a little bit because there's a whole section dedicated to the derivative of the logarithm function. And that's coming up, I think, in a week or so. But I just wanted to give you an example that you can derive functions that you don't really understand and just write it as the derivative of that, whatever that may be. Okay, so now let me talk about a little bit about implicit functions. That's the next ingredient. What is an implicit function? Well, here's the thing. Suppose that you write the equation x squared plus y squared is equal to 1. Just think about this as an equation for now. Don't think about y as a function. Think about y as just a variable. What does that equation represent? What is that? A circle, right? So everybody knows this thing is a circle of radius 1. Okay, but let's think about exactly what that means. What is the relation between this equation and this circle? Can anybody tell me exactly what that relation is? When you think about this equation, you think about the circle, but what does that mean? Pilar? What do you think? No? What is the relation between... Okay, Pilar, so the question again is, what is the relation between this equation and this circle? Everybody knows that this is the equation of a circle, but what do you mean by that?
I mean, isn't it just y? I don't know, we always just knew it was something.
You always know it's a circle, okay. What does that mean? Can somebody tell me? Yiming? Are you Yiming? No? Where is Yiming? Yiming Wang? No? Okay. How about Tolu? Okay. Okay, Eric, what's the relationship between that equation and that graph?
Well, I would assume that the equation is the algebraic representation of every single point that lies on the line that you draw to make the circle, I guess. I don't know how to put that into.
Okay, I'm going to paraphrase Eric. Because I think you got the right idea, but didn't quite understand what you said. But I think it's true.
Okay, it's Friday morning. I don't have to make sense.
Friday morning, yeah. Well, okay. So basically, think about this line over here. What would be a point? Let me just any point on the line. For example, the point 1, 0, right? This point over here, 1, 0. Does it satisfy the equation if you plug in 1 here and 0 here? This is equal to 1, right? Okay, what about the point minus 1, 0? Same thing, right? Point 0, 1, point 0 minus 1, they all satisfy the equation. Well, as a matter of fact, the equation, I may be saying something obvious, but I think it's good to remind you guys, the equation has a set of points x, y that satisfy the equation. I cannot just plug any x and any y and get 1. But there are some points x and y that if I plug them in, that gives me 1. And those points lie on the circle. In other words, the circle is a set of points x, y that satisfy that if I plug them in this equation, the left-hand side is equal to the right-hand side. That's the relationship between the equation and the graph. Let me say that again. The graph, the circle, is a set of points x, y that satisfy the equation algebraically. Or the set of points such that x squared plus y squared is actually equal to 1. Okay, now that we got that out, just wanted to remind you because sometimes it's not obvious to people. I would like to say, well, there are some functions. Let me draw a function that happens to lie on the equation, on the graph. For example, this one right here. It's a little hard to see, but the whole circle is not a function. You guys know, right? The whole circle would not be a function. But you can just take the top part of that circle, and that is a function, right? Okay, so if you call that function y of x, then y of x satisfies function y of x satisfies x squared plus y of x squared is equal to 1. It satisfies the equation. Okay? Now, let's suppose, in principle I can solve for y. It's actually not that hard. But without solving for y, let's find out the derivative of y. You might say, well, how are you going to find a derivative if you don't know the function? Well, that's the whole point. We can actually derivate on both sides to find out the derivative of the function y, even if I don't know exactly what y is. Let's do this. Derivate on both sides, and I get 2x plus, and what is the derivative of y of x squared? Well, again, it's a chain rule problem, right? The outer function is x squared, the inner function is y of x. So the derivative of that is 2 times y of x times y prime of x, and that thing is equal to 0. Great. I'm just going to leave it at that for now. So what I want to point out is that some functions can be defined implicitly in terms of an equation, and that you can actually derivate on both sides to find information about the derivative, even if you don't know the function itself. Let me give you another example. This ellipse, let's say, no, actually here, this one here. X to the 3 plus y to the 3 is equal to 6xy. Okay, this is another equation, and just like the previous equation, we can draw on the plane the set of points x and y that satisfy the equation. In this case, those points lie on a much stranger curve, something like this. Weird, right? So that's a much more strange looking graph than the previous one. But it doesn't matter. We still have a very simple equation that we can derivate on both sides. Now what happens with this equation? This equation implicitly defines a function y. For example, if I draw a function over here, this function right here, let's say from here to here, is implicitly defined by this equation. This equation implicitly defines the function y of x in the graph. Okay. Now, the difference is that now we cannot solve for y. As a matter of fact, we can, if you fire up a computer, you're going to get a very long and complicated expression that's actually on the book. It fills up a whole line of the book, full of square roots and squares and whatnot. So it's possible to solve for y, but it's very, very hard. And you don't want to derivate that by hand. It would be a huge mess. Okay? But nevertheless, we can derivate this expression on both sides, and it's going to tell us information about the derivative of that function. Okay? So let's not do the derivative for now. I just want to point out what an implicit function is. So that's the first part of this section, is to understand what an implicit function is. And the derivative part is actually relatively easy compared with this. So what do you think? Is this idea clear? You got some equation, and you got a graph. The graph defines some function y, right, that is implicitly defined by the equation. Is that weird, or is it okay? What do you think? Okay. I can give you a whole bunch of more examples. You can draw the weirdest equation you want. You can imagine the set of points that's satisfied, and this equation defines implicitly a function. Basically, any function that lies on the equation, any function that lies on the graph. You can talk about it as implicitly defined. Okay, so sometimes we can solve for y, sometimes you cannot. Sometimes we cannot. So, okay. So now let's start derivating more systematically those implicitly defined functions. Let's see. So let me draw this this curve here. Okay, this is an ellipse. This is the point 3, and this is the point 1. And does anybody remember from, I don't know, pre-calc, I don't know what that would be, what class that would be, what equation represents this ellipse? Implicitly what equation represents the ellipse? Well, it's a lot like x squared plus y squared is equal to 1. Except that we divide by 1 here and by 9 here. This 9 is actually 3 squared. Okay, the reason it's a 9 is because, oh wait a minute, did I do this wrong? Yeah, hold on. Yeah, you're right. Thanks. This is a 1. Okay. Y squared over 1 is equal to 1. Okay. So now, again, this 9 is basically 3 squared, and that represents this this value here. And the 1 is essentially 1 squared. It represents this value over here. That is the equation of an ellipse. Okay. So we have an implicitly defined function by this equation. We're going to derivate on both sides to find out the derivative of that implicitly defined function. Okay, so what do we get? Over here we get 2x divided by 9 plus, and now what's the derivative of y squared? Remember, y is a function y of x. We don't know exactly what it is. It's implicitly defined by this equation. But just think about it as a function y of x. What is the derivative of y squared? Yes?
2y times y prime.
Absolutely right. So the derivative of y squared is 2y times y prime. It looks really compact. Really what we're doing is we're using the chain rule. We're thinking the outer function is x squared, the inner function is y of x, and so we're derivating the outer function and evaluating at the inner, and then we're multiplying by the derivative of the inner. Okay, this whole thing is equal to 0 because the derivative of 1 is 0. All right, so now we can solve for y prime, and we get something like y prime is equal to minus x over 9. Okay, so I cancel the 2 on both sides. Oh, sorry, I still have to divide by y. So y prime is equal to x over 9 divided by y. There you go. Okay. So, but you say, what does this really mean? I mean, we don't know why. So, does it say anything? Well, as a matter of fact, it does. This expression can be used by itself. But let's just leave it like that for now. Well, okay, let's use it for something. Okay, so for example, okay, let's take a point that's actually on the line. For example, this point right here. Let's say that this is 1. If the x value is 1, what is the y value? What do you think in this case is the y value? Two? I don't know. Let's say 1 squared over 9 plus y squared over 1 is equal to 1. That means that y squared is equal to 8/9 and y is equal to square root of 8 over 3. Okay? So the point 1 comma square root of 8 over 3 lies on the graph of y of x. Okay, find the slope of y at that point. So in other words, we want to find this slope right here. Okay? So you say, well, this formula here that seemed so abstract and not so clear what it can be useful for, well, you simply plug in the values of x and y to find the derivative. So m is equal to y prime of 1 is equal to minus 1 minus 1 divided by 9 y of 1, and that's equal to minus 1 divided by 9 times square root of 8 divided by 3. So there you go. The slope of the function at that point is minus 1 over this expression. That's equal to minus 1 over 3 square root of 8. Okay, awesome. Let's do another example of this. Let's go back to our weird looking donut shaped, well, I'm not sure if it's a donut, but this thing over here. How would you describe that? A loop. Okay? So let's go back to our loop. And so this is the equation x squared x to the 3 plus y to the 3 is equal to 6xy. Problem is, find the slope at the point 3, 3. So this is supposed to be the point 3, 3. We are being told that the point 3, 3 is actually part of the graph. Let's verify that that is actually true. So let's start by verifying that this point is on the graph. So first, verify point 3, 3 lies on the graph. And how do I verify that the point 3.3 is on the graph? Well, I simply look at the points x equals 3, y equals 3, and I plug them into the equation to see if the left side is equal to the right side. So that's 3 to the 3 plus 3 to the 3 is equal to 6 times 3 times 3. Is that true or not? What do you think? It's true, right? I can cancel out this 2 3's and these here 2 3's and here 2 3's. I get 3 plus 3 equals 6. Okay? So that's good. Fortunately, the point is actually on the line. Okay. Now, let's take the implicitly defined function. So derivate on both sides where y is an implicitly defined function of x. So let's see, we get, on this side we get 3x plus, what is the derivative of y to the 3? Let's see. Do you want to try? The derivative of y to the 3? What is the derivative of y to the 3? Yes, sir?
3y squared dy dx.
Yes. Thank you. This would be 3y squared. Let's call this just y prime. What?
Last line is squared.
Oh, yes. Thank you. Thank you. Sorry. 3x squared plus 3y squared times y prime is equal to, and now what do we do with the derivative of 6xy? It's a product rule, that's right. So I'm going to write this as the product of 6x with the function y. In other words, I'm going to think about the function 6x and the function y, and I'm going to multiply them, and the derivative of that is 6x times y prime plus the derivative of 6x, which is 6 times y. Okay. Let's see. So let's solve for y prime to find the derivative y prime in terms of x and y. And for that, well, actually, the first thing we can do is we can cancel out 3's all over the place. So actually, I get x squared plus y squared y prime is equal to 2x y prime plus 2y. Okay, and I can, let's say, write x squared minus 2y is equal to 2x y prime minus y squared y prime. I simply brought this to this side and this guy over to this side. And now I'm going to factor out 2x minus y squared, and I'm going to divide on both sides. And I get x squared minus 2y divided by 2x minus y squared is equal to y prime. Awesome. So now you might think, well, what's this useful for? Well, remember, what we're trying to do is to find the slope of this graph at the point 3, 3. So we defined our function y of x implicitly using this formula. We derivated on both sides, and now we know the derivative. But what do we do with this expression? Well, we know that the point 3, 3 is on the graph. In other words, we can plug in x equals 3 and y equals 3, and we get the slope at 3, 3. We have 3 squared minus 2 times 3 divided by 2 times 3 minus 3 squared is equal to, what is that? That is 9 minus 6 is 3, and this is 6 minus 9 is minus 3 is equal to minus 1, and that is the slope, that is y prime at the point 3, 3. That means that tangent line looks something like this, with m equals minus 1. Okay, so that was a very practical use of implicit functions. We derivated the implicit function on both sides. Do you have any questions? Questions? No? You good? Okay. So now we're going to be using implicit differentiation to find out some new derivatives. Just like we found out the derivative of logarithm of x, we can find out the derivative of inverse trigonometric functions. Okay, so inverse trigonometric functions. Suppose that, let's say, suppose we're going to find a derivative of y of x equals sine minus 1 of x. All right, sine minus 1 of x is the inverse function of sine of x. We've already plotted it before. Now I would like to find a derivative of this function. Yeah, this is a trig, not trick. Okay, so suppose that y of x is equal to sine squared of x. Now, we already know this formula here. The sine of sine minus 1 of x is equal to, what is that? X, that's right. Why is that? Because sine and sine minus 1 are inverses, right? So they cancel each other out. Okay. So sine of y of x is equal to x, where y of x is the function defined by this expression, sine minus 1 of x. Okay? So, once again, let's think about y as implicitly defined function of that equation, the equation sine of y equals x. We're going to derivate on both sides. Okay? So, let's do it. Let's derivate on both sides. This is a chain rule. The outer function is sine of x. The inner function is y of x. So, what is the derivative of this expression over here? What do you think? It's cosine of the inner multiplied by the derivative of the inner, y prime of x, is equal to 1. You got it. Okay, now I'm going to step back a little bit. I'm going to go to an identity that you guys are already familiar with. Recall the identity that sine squared of alpha plus cosine squared of alpha is equal to 1. Okay, so that means that you can write cosine of alpha as the square root of 1 minus sine squared of alpha. Okay, just simplify, solve for, basically bring the sign over to this side and take square root on both sides. So I'm going to go back to the equation above, and I can write this cosine of y of x times y prime of x. I can write this down as the square root of 1 minus sine squared of y times y prime of x, and that is supposed to be equal to 1. Okay, so basically what I did here is I replaced cosine of y with square root of 1 minus sine squared of y using this formula over here. Okay? All right. So y of x has a particular property. Y of x satisfies that sine of y is equal to x. So what is sine squared of y of x? Seems a little bit tricky because sine of y, we agree sine of y is equal to x. What about sine squared of y? Okay, remember that sine squared of y is a notation for sine of y squared, right? This thing is the same thing as sine squared of y, sine of y, the whole thing squared. But sine of y was x, right? So the whole thing is just x squared, right? So this is 1 minus x squared times y prime of x is equal to 1. Was that clear why that is 1 minus x squared? Should I say it again? No? Yes? No? Okay, all right, great. All right, so then we're getting awfully close to an actual derivative, to an actual expression for y prime, because I can divide on both sides and I get y prime of x equals 1 over square root of 1 minus x squared. And this is the derivative of sine minus 1 of x. I was always surprised by this formula. Actually, I still am. If you got a whole bunch of trig functions, sines, cosines, sine minus 1, how is it possible that you derivate a trig function and you get a rational function or some algebraic function? You would think that these functions are all trigs. If you derivate a trig like sine, you get a trig function. If you derivate cosine, you get a trig function. How is it possible that you get a rational function or something that doesn't have any sines or cosines when you derivate that? I mean, here's the answer. I still really don't get the intuition why it shouldn't involve sines and cosines, but there it is. So the derivative of this inverse trig function is that. Questions? No questions. What about, let's do another one. Let's do the derivative of the tangent function. Okay. So the first thing we do is we define y of x equals tangent minus 1 of x. So what formula or what equation does y of x satisfy? And the formula that y of x satisfies is that the tangent of y is equal to x. That's right. Okay. So let's see. Why is tangent of y of x equal to x? Does anybody wanna? Yeah, do you wanna try? Why is yes? Why is tangent of y? Yes.
Oh, because y, the function y is inverse tangent.
Okay.
Tangent times inverse tangent.
Okay, so there you go. So that's because the tangent inverse function cancels out with the tangent function and you just get the x. Okay, same as before. So now let's think about, forget about what y is. Let's think about y as an implicitly defined function of this equation. Just forget about what it is. Just think about it as y of x. We're going to start manipulating this function algebraically without really worrying about where it came from. So I'm going to derivate on both sides this expression, and the outer function is tangent, the inner function is y. So the derivative is secant squared of y times y prime is equal to 1. If you want, you don't have to write the x. Sometimes the book just doesn't write, just writes secant squared of y times y prime equals 1. Okay. Now we're going to have to come up with some trig identity that can replace secant squared with something in terms of tangent. So I'm going to basically talk about something slightly different for a moment. You know that sine squared of alpha plus cosine squared of alpha is equal to 1. I'm going to I'm going to multiply on both sides by 1 over cosine squared of alpha. Over on this side and on this side too. What happens when I do that? Well, on the right hand side I get 1 over cosine squared of alpha, which is secant squared, right? And on the left hand side I get sine squared over cosine squared, which is tangent squared, plus cosine squared over cosine squared is 1. Okay, so tangent squared of alpha plus 1 is equal to secant squared of alpha. Great. So that means that secant squared is equal to tangent squared plus 1. All right, so back here, secant squared of y is equal to tangent squared of y of x plus 1 multiplied by y prime of x is equal to 1. And remember, this thing is nothing other than tangent of y squared. Right? This is just shorthand notation for tangent of y squared. But tangent of y is x. Right? Tangent of y is x. So tangent of y squared is nothing other than x squared. Okay. Therefore, y prime, or the derivative of the tangent minus 1 function, is 1 over x squared plus 1. See, we're getting all kinds of fun identities from this, from these implicit functions. Do you have any questions? Okay, let me see. We have 5 minutes left. Maybe we can talk about a question from the exam. What do you think? Would you like me to do another question from the exam to find out how it is? Or do you have any questions about implicit differentiation? Kendrick? No questions? Okay. All right, then let's do a problem. We still have like 5 minutes to go. Well, more like 3 minutes. We're going to call it a day then. Thanks. See you Monday.